All right, so what do we need to do in order to make recursion actually work? So in our code, there's going to be two things that we need to basically always make sure we do, right? Otherwise, things will not work out too well for us. The first thing, right, is basically have some sense of progress. So we have this idea, right, of a whole problem, which becomes a subproblem, and a subproblem maybe has a subproblem of its own, subproblem of its own, and eventually, right, you get to a base case. Right, that's kind of the basic idea we had from the previous video. We need to basically make sure this process happens, right? We need to make sure that we have progress. We need to be making progress towards a base case. If we're not, then things are bad. So if I have basically, things being regenerated, like for example, let's say here, right, the problem got smaller, right? So like this was okay, this is okay, but all of a sudden, if this one over here, right, so this subproblem is actually the same as this one, what I've created is a loop, right? And all of a sudden, it's like I won't get to that base case. I'll just go back. It's like, oh, I have the same thing, same thing, same thing, same thing. I get stuck, right? So I can't have this situation where it's like, well, I have the exact same problem as the one that I put in, right? It needs to always get smaller. I need to be making progress towards the base case. If I don't do that, right, if I don't make progress, all of a sudden, I'm not going to actually get to the base case. I'm going to get stuck somewhere along the lines. I'm not going to get there. I'm not going to terminate. I'll just continue trying to do work, but kind of just spinning my wheels. Nothing's really happening. The goal, of course, is to guarantee termination, right? We need to make sure we get to the end. If we don't terminate, then we never return a result and nobody gets to get back the answer to their problem, right? I've effectively done no work, right? I have infinite recursion. Probably there'll be something in my programming language that'll complain that, oh, hey, there's a stack overflow, right? There's too many function calls. It's not going to work. All right, so those are two things that I need to do, right? And this is actually for all algorithms. This is actually kind of key. All algorithms, recursion or otherwise, should always make progress towards some termination condition, right? If you don't have that, you basically have algorithms that run forever and don't actually get you back a result. So this is a very general rule. All right, some other stuff to watch here. Basically, right, we talked about this already, right? We need to make sure we're making progress, don't stay the same. Second thing, right, is we need to not change our problem. So here, right, it's like I have cloud box. Well, all of a sudden, right, if I do that, I can't, solve my, well, all of a sudden, if I do that, basically, I get stuck, right? So you can imagine, if I have, some function to draw clouds, it's like, well, I called on the outside, then it runs, it calls itself again, calls itself again, calls itself again, right? Methods calling methods. But if I get to this box, right, if I get to something completely different, I can't call that method anymore. It's like you can imagine you're making a recursive call and you're passing it strange parameters. If you do that, it's just going to break, right? You're going to not be able to solve that problem anymore because all of a sudden you changed how it looks. So as you kind of work through this, right, your whole problems and your subproblems, right, those should always be the same type of problem, right? What's different is the size, right? The size is different, right? It's like here it's 5, that's 4, then it's 3, then it's 2, right? That's what's different. Just the size, the type of the problem itself should still be the same. So in general, recursion is very important. So recursion, well, this is a very long story here, but basically recursion is everything, okay? So at the end of the day, if you were told to have one piece of paper which contains all the rules from which everything else in computer science or software engineering, are derived, the only thing you need to write down there is the idea of recursion, okay? If you look at, and this is more advanced, but there's this idea somehow of models of computation. Like how do we define a computer, right, that can do work, right? We can say, oh, what type of computer is this? What can it do, right? You have different computers, you can compare them. The most kind of simplest one, right, the one that's I guess the most simple as well as the most general, is one basically just built on recursion, because it turns out that recursion can be used to do pretty much anything. We're used to doing things like using loops all the time. Turns out that recursion is actually can be used to fulfill the same need as a loop, right? It can replace it, because recursion is all about repetition. Recursion is very, very general. I'm really not doing it justice here, but truly recursion is one of the few top level problem solving techniques that we have, right? Basically, you can do anything you can do kind of with a standard programming language, right? You can think about calling functions, having loops, all this stuff, right? There's a way somehow to implement that by just having recursive functions, okay? It's a little bit tricky to do sometimes, but they are that powerful. All right. So the question here, or the remark here, is that and this is just a side note more than anything else for you guys, there's a special type of recursive call where basically I have like a function or a method, and it calls itself only once in the very last line. That's called tail recursion. Because what you can think about, and I guess I'll do a quick diagram here, whereas I can have something like this. I can have a function A. So function A. Let me redraw it. Okay, so I have function A, no parameters. Actually, I should have a parameter, and otherwise, if I don't have a parameter, then that means there's nothing that I'm working on, right? There's nothing for me to solve. And it could be that, A is either looks like, well, let's do B over here. I'll do B as well. So I'll do B first. So B perhaps could be, I could do print n, and then over here I could do n minus 1. So like, okay, right-hand side, b of n is a function. First thing is it prints n, then it calls itself on n minus 1. Versus over here I could have maybe these orders switched. So I could call a of n minus 1, and then print of n. So if I were to do it that way, so this one, well, they're both recursive, right? They both have basically something calling itself. They're incomplete though. I'm missing the base case. There's no way for these to terminate. But if I were to have these up, right, the way I'd call these is this is just normal recursion versus this is tail recursion. Tail recursion, I don't have space. So what do we care? Well, for us, I guess it won't mean all that much, but somehow right inside what matters is that tail recursive calls like this one are easier to optimize. So if you were to write basically two functions, right, they use these two different kind of orderings of either have recursion anywhere, which is what this is, or have recursion only at the end, the one that has it only at the end will be faster. Okay, so it's something we can do for optimization. Now for us, we don't care too much, and maybe some of our compilers won't even use it, but it is something right there that we should know about. Right, so tail recursion is something a recursive method that only calls itself once, and it's in the very end of it. So why do we need recursion? Well, recursion basically is a handy way to solve problems. So there are problems that basically are very natural to do. Now, you guys have already seen data structures like, for example, a list. A list looks something like this, where I have these different nodes. Maybe I have a head over here, and well, what happens is well, this is a recursive structure. Okay, so I have nodes. So nodes look like basically. So a list is basically. So a list is either null or a node linked to another list. Okay, so lists themselves are recursive. So when we have like a recursive data structure, it makes sense to have a recursive method that goes and does stuff like, for example, printing it out. And indeed, that'll be one of our examples later on. So anytime we have basically data structures look recursive, they look recursive. So anytime we have data structures that look recursive, it makes sense for us to write recursive methods to go and do operations on them. It ends up being a very natural thing to do and much easier to do than using iteration.